9 in the morning, June 1940. The Armored Maneuver Grounds at Fort Knox, Kentucky. The temperature is already climbing toward 90 degrees. 9 in the morning, June 1940. The Armored Maneuver Grounds at Fort Knox, Kentucky. The temperature is already climbing toward 90 degrees, and the dust from the tracked vehicles hangs in the humid Kentucky air. A column of M2 light tanks is attempting to execute a coordinated maneuver, a simple wheeling movement that requires the tanks to turn together, maintain their intervals, and respond to commands from the company commander. The commander, a captain standing in the open turret of the lead tank, is trying to control his unit by radio. He keys his microphone and gives the order to turn left. 3 of the 8 tanks turn left. 2 continue straight. 2 turn right. 1 stops entirely, its commander leaning out of his hatch, trying to figure out what the order had been. The radio in the captain's tank, an SCR-245, is producing a wall of static so dense that his transmission is barely intelligible to the tanks more than a few hundred yards away. The static comes from the tank's own engine, its ignition system, its generator, the electrical noise of the vehicle itself, flooding the amplitude-modulated radio signal with interference that no amount of shouting into the microphone can overcome. The captain gives up on the radio. He climbs out of the turret, stands on the engine deck, and begins signaling with hand flags, the same way cavalry officers had signaled their troops for the previous 200 years. The tanks, watching for the flags, slowly reassemble into formation. The maneuver that should have taken 2 minutes takes 15. And the captain, climbing back into his turret, understands something that the entire United States Army armored establishment is in the process of understanding in the summer of 1940. The American tank radio does not work. It does not work well enough to control a tank unit in motion. It does not work well enough to do the one thing that makes a modern armored force more than a collection of individual tanks, which is to coordinate them, to make them maneuver and fight as a single coherent body responding to a single commander's will. The Germans, who have just finished demonstrating in Poland and France exactly what a properly coordinated armored force can accomplish, have radios that work. The Americans do not. And the reason the Americans do not is buried deep in the physics of how radio signals are transmitted, in a technical choice between 2 ways of encoding sound onto a radio wave that the United States Army has not yet made, and the German Army has not made either, but that an American professor of electrical engineering at a small agricultural college in Connecticut has already figured out. The German demonstration of armored warfare in 1939 and 1940 had stunned the world, and most observers focused on the tanks themselves, on the panzer divisions, on the concentration of armor and the speed of the advance. But the military professionals who studied the German success most carefully understood that the tanks were only part of the story. The deeper innovation was coordination. German tanks could talk to each other. Every German tank carried a radio receiver, and command tanks carried transmitters, and the German doctrine of armored warfare was built on the assumption that a tank unit could be controlled in real time by its commander through continuous radio communication. The German commander, Heinz Guderian, who more than anyone had built the German armored force, had begun his career in signals, in communications, and he understood from the beginning that the radio was as important to armored warfare as the gun or the engine. A tank that could not communicate was a deaf and mute weapon, fighting its own private battle, unable to combine its action with the tanks around it. A tank that could communicate was part of a coordinated machine that could concentrate its force, exploit opportunities, and respond to a changing battlefield faster than an enemy who lacked equivalent communication. The United States Army understood this in principle. The American Armored Force, formally established in July of 1940, had absorbed the lessons of the German campaigns. American officers knew they needed radio-equipped tanks, coordinated by radio, fighting as integrated units. The problem was that the radios the United States had were not good enough to do the job. The standard American tank radio of 1940, the SCR 245, was an amplitude modulated set, an AM radio, and AM radio had a fundamental physics-level vulnerability that made it nearly useless inside a tank. That vulnerability was interference. And the solution to it, frequency modulation, was a technology that existed, that worked, and that almost nobody in the American military establishment had yet recognized as the answer to the tank radio problem. This is the paradox at the center of the story. The United States in 1940 was the most electrically sophisticated society on Earth. It had more radios per capita than any other country. It had built the world's largest commercial broadcasting industry. It had companies like RCA, like General Electric, like Westinghouse, that employed thousands of the world's best radio engineers. American homes were full of radios. American cars increasingly had radios. The country that would shortly build the proximity fuse, the SCR 584 gun-laying radar, and the electronics for the atomic bomb was, in raw electronic capability, second to none. And yet the United States Army, in 1940, could not equip its tanks with radios that worked well enough to coordinate an armored attack. The most electronically advanced nation on Earth had tank radios that forced their commanders to fall back on hand flags. The resolution of this paradox lay in a gap between civilian capability and military application. The radio engineering existed. The specific solution to the tank radio problem, frequency modulation, existed and had been demonstrated, and was being deployed in a few specialized civilian applications. But it had not yet been transferred into military equipment, because the military procurement system was slow, because the relevant engineers worked in the civilian sector, and because the entire effort of converting civilian electronic knowledge into military electronic equipment was just beginning in 1940. The story of how the United States got working tank radios is the story of that conversion, of how the civilian radio industry of the American Midwest, centered not in Detroit exactly, but in the broader industrial heartland around Chicago, learned to build military electronics at scale, almost overnight, and produced the FM combat radios that allowed American armored and infantry units to fight as coordinated bodies for the rest of the war. The man at the center of that story was not a soldier. He was a professor who had taught himself FM radio building a college radio station and a state police communication system, and who joined a struggling Chicago manufacturer just in time to solve the United States Army's communication crisis. The popular history of the Second World War has almost nothing to say about tank radios. It has a great deal to say about tanks, about their guns and their armor and their famous battles. It has essentially nothing to say about the radios inside the tanks, even though those radios were, in many respects, more decisive than the guns. A tank's gun affected the outcome of a single engagement. A tank's radio affected whether the tank could be part of a coordinated force at all, which affected the outcome of entire campaigns. The radio was the difference between a tank that fought alone and a tank that fought as part of a team, and the team almost always beat the individual. But the radio was invisible, hidden inside the turret bustle, producing nothing photogenic, attached to no famous battle, and so it dropped out of the popular history almost entirely. The men who designed and built the American combat radios are even less known than the radios themselves. Daniel Noble, the professor who became the chief engineer of the effort, is not a household name. Henryk Magnuski, the Polish immigrant engineer who designed the radio frequency circuits, is not a household name. Paul Galvin, the businessman who bet his company on military electronics, is remembered, if at all, as the founder of Motorola, with little attention to what Motorola actually did during the war. The engineers and the assembly workers, mostly women, who built hundreds of thousands of combat radios in factories around Chicago and across the Midwest, are entirely anonymous. They produced the nervous system of the American ground forces, the communication network, that allowed American units to coordinate, and they did it in a few years, building an entire military electronics industry essentially from scratch, and they are absent from the story that the popular history tells about how the war was won. To understand why American tank radios failed in 1940 and why FM radio solved the problem, you have to understand the difference between amplitude modulation and frequency modulation. Both are methods of encoding sound onto a radio carrier wave. Amplitude modulation encodes the sound by varying the strength, the amplitude of the carrier wave. When the sound is loud, the wave is made stronger. When the sound is soft, the wave is made weaker. The receiver detects these variations and reconstructs the sound. This is how AM radio works, and it works well enough for commercial broadcasting in most conditions. The fatal weakness of amplitude modulation is that electrical interference also affects the amplitude of the radio wave. Every electrical spark, every ignition pulse, every generator brush, every electric motor produces bursts of electromagnetic noise, and that noise adds itself to the amplitude of any AM signal passing through. The receiver cannot distinguish between amplitude variations that represent the intended sound and those that represent interference. It reproduces both. Inside a tank, this is catastrophic. A tank is one of the noisiest electrical environments imaginable, with an ignition system producing thousands of sparks per minute, a generator, electric motors, switching equipment, all producing continuous electrical noise. An AM radio inside a tank is drowned in interference from the tank's own electrical system, and the intended voice signal is buried under the static. This was exactly the problem the captain at Fort Knox experienced. Frequency modulation solved the problem by encoding the sound a different way. Instead of varying the amplitude of the carrier wave, FM varies its frequency, shifting the wave slightly higher and lower to encode the sound while keeping the amplitude constant. The receiver is designed to ignore amplitude variations entirely and to respond only to frequency variations. Because electrical interference primarily affects amplitude, an FM receiver can simply discard it. The voice signal, encoded in the frequency, comes through clean. This property of FM, its rejection of amplitude-based interference, was exactly what a tank radio needed. The physics that made FM superior for tanks had been understood, in theory, since the work of Edwin Armstrong, the American engineer who invented wideband FM in the early 1930s. But translating that theory into a rugged, mass-producible military radio was a separate problem, and it was that problem that the American radio industry had to solve in 1940 and 1941. The American tank radio of 1940 was the SCR-245, an amplitude-modulated set that had been standardized in 1937. It was one of the first crystal-controlled radios the Army had adopted, which gave it accurate frequency control, but it was an AM set, and it suffered from all the interference problems that AM radio suffered from in the electrical environment of a tank. It was also bulky, mechanically fragile, and difficult to tune precisely. The crews disliked it. The commanders found it inadequate for controlling units in motion. It had replaced even older sets, the SCR-293 and others, that were worse. The entire lineage of American tank radio, up to 1940, was a lineage of AM equipment that did not adequately solve the fundamental problem of communicating from inside an electrically noisy armored vehicle. The Army knew it had a problem. The newly formed armored force, established in July of 1940 under General Adna Chaffee, made tank radio a priority. The Signal Corps, which was responsible for Army communications equipment, began looking for a better solution. The question was what technology to adopt and which manufacturers could build it. The answer, frequency modulation, was becoming clear to the technically informed officers in the Signal Corps, but FM was a new and somewhat controversial technology in 1940. Edwin Armstrong had been fighting commercial and patent battles over FM for years. The established radio industry heavily invested in AM, had resisted FM. Adopting FM for military radio meant betting on a technology that the mainstream of the American radio industry had not fully embraced. It also meant finding a manufacturer who actually understood FM well enough to build military equipment, and in 1940 that was a short list. Because FM was so new that few companies had practical experience with it. One of the few people in the country who had built working FM systems, who understood the technology not as theory but as practical engineering, was a professor at the University of Connecticut named Daniel Noble. Daniel Earl Noble was born on the 4th of October 1901 in Naugatuck, Connecticut, a small industrial town in the Naugatuck River Valley. He came from modest circumstances and worked his way through college at the Connecticut Agricultural College, which would later become the University of Connecticut. As a student, in 1922, Noble built and put on the air the first college radio broadcast station in the country. An extraordinary accomplishment, given that commercial radio broadcasting itself was only 2 years old at the time. His station broadcast 3 times a week, an hour at a time, with weather reports, information for farmers, and concerts from the campus. In 1925, it broadcast its first basketball game, the college playing Trinity. Noble had taught himself radio engineering by doing it, by building transmitters and antennas and receivers and putting them on the air, learning the practical realities of radio in a way that no textbook could teach. After graduating, Noble pursued advanced study, attending Harvard and earning a graduate degree from the Massachusetts Institute of Technology, eventually holding a doctorate in electrical engineering. He returned to Connecticut to teach at his alma mater, where he continued to develop the college radio station and to expand his expertise in the new field of frequency modulation. 2 Hartford radio stations, WTIC and WDRC, sought him out to build relay stations, and for one of them, Noble built one of the first commercial FM broadcast stations in the country. By the late 1930s, Daniel Noble was one of the most experienced practical FM engineers in the United States, a man who had not merely studied FM, but had built FM stations and made them work. This practical FM expertise was rare, and it was about to make him exactly the right person to solve a problem that the United States Army did not yet fully know it had. The achievement that made Daniel Noble's reputation and that attracted the attention of both industry and the military was the Connecticut State Police radio system. In 1939, Edward J. Hickey, the commissioner of the Connecticut State Police, asked Noble to design a mobile radio system for the state police. Police radio, at the time, was almost entirely one-way and amplitude modulated. A dispatcher could broadcast to patrol cars, but the cars could not easily talk back, and the AM signals were plagued by the same static and interference that plagued all AM mobile radio. Hickey initially suggested a one-way system, the standard approach. Noble, who had designed 2-way AM units and built FM broadcast stations, recommended something far more ambitious. He proposed a 2-way, frequency-modulated system in which every patrol car could both transmit and receive, with the FM technology rejecting the electrical interference that crippled AM mobile radio. Noble designed the entire system. He originated the system's planning, and he personally supervised every phase of site selection, equipment testing, and design detail. The system was completed in 1940, and it worked. It was the first 2-way state police radio system ever placed in operation, and it was the first practical 2-way FM mobile radio telephone system in the world. The interference that had plagued police radio vanished. Patrol cars could communicate clearly in both directions across the state. The Connecticut system was a landmark achievement in mobile communications, and word of it spread quickly through the small world of American radio engineering. It demonstrated, conclusively, that FM was the answer to mobile radio interference, that a 2-way FM mobile system could be built and could work reliably in the real world. And it demonstrated that Daniel Noble was the man who knew how to do it. Among those who took notice was Paul Galvin, the founder of a Chicago radio manufacturer called the Galvin Manufacturing Corporation. The Galvin Manufacturing Corporation had been founded in Chicago in 1928 by Paul Galvin and his brother Joseph. Their first product was a battery eliminator, a device that allowed battery-powered home radios to run on household electric current. The business was modest and precarious through the early years. Galvin's breakthrough product came in the early 1930s when the company developed an affordable car radio. Putting a radio in an automobile was a difficult engineering problem because the car's electrical system produced interference, and the vibration and temperature extremes of automotive use destroyed delicate radio equipment. Galvin's engineers solved these problems well enough to produce a commercially viable car radio, which they named the Motorola, a coined word combining motor for the automobile with ola, a suffix associated with sound, as in Victrola. The Motorola car radio was a success, and it gave the company both a profitable product line and, crucially, deep practical experience in the specific problem of making radios work in the electrically hostile, mechanically punishing environment of a motor vehicle. This experience, building radios that worked in cars, was directly relevant to the problem of building radios that worked in tanks. A tank was, electrically and mechanically, an extreme version of an automobile, noisier, rougher, hotter, more demanding. The Galvin Company's years of experience solving automotive radio problems had given it exactly the engineering culture needed to tackle military vehicle radio. When Paul Galvin recognized that the coming war would create enormous demand for military electronics, he positioned his company to meet it. The most important single thing he did was to recruit Daniel Noble. In 1940, impressed by Noble's Connecticut State Police FM system and recognizing that FM was the future of mobile communication, Galvin hired Noble away from the University of Connecticut to serve as the company's director of research. It was a pivotal decision. Galvin was betting his company's future on military electronics and on FM, and he had just hired the man who understood FM mobile radio better than almost anyone in the country. In 1941, the Galvin Manufacturing Corporation reincorporated under the name of its most famous product. It became Motorola. Daniel Noble assembled a team of engineers to develop the military FM radios that the Army needed. The team included some remarkable individuals. The principal radio frequency engineer was Henryk Magnuski, a Polish electrical engineer who had fled Poland after the German invasion in 1939. Magnuski had been a brilliant young engineer in Poland, working on radio and communications, and when his country was overrun, he made his way to the United States, where he found work at the Galvin Company. He became the lead RF circuit designer for the military radio program, responsible for the radio frequency stages that determine the performance of the radios. Magnuski was an immigrant, a refugee from a country the Germans had just destroyed, and he poured his expertise into building the radios that would help the American Army defeat the same enemy that had driven him from his home. Other members of the team included Marion Bond, Lloyd Morris, and Bill Vogel, engineers who worked on various aspects of the radio designs. The team's most famous product would be the SCR-300, the backpack FM radio for infantry that became known as the walkie-talkie. But the broader effort encompassed the whole family of military FM radios, including the vehicle radios for tanks and armored vehicles. The engineering challenges were formidable. The radios had to be rugged enough to survive the vibration and shock of vehicle and combat use. They had to operate over wide temperature ranges. They had to be simple enough that ordinary soldiers could operate them. They had to be manufacturable in enormous quantities. And they had to use FM in frequency ranges where it had never been used in mass-produced military equipment, requiring new circuit designs, new components, and new manufacturing techniques. Noble's team, drawing on the company's automotive radio experience and on Noble's and Magnuski's FM expertise, solved these problems and produced radios that worked, that were rugged, and that could be built by the hundreds of thousands. The radio that answered the tank communication problem was the SCR-508. It was standardized on the 22nd of July 1941, and it represented the United States Army's commitment to both frequency modulation and crystal-controlled tuning for armored communications. The SCR-508 was an FM radio, operating in the frequency range of 20 to 27.9 MHz. It consisted of a BC-604 transmitter and two BC-603 receivers mounted on a common tray, the FT-237 mounting tray, which was installed in the turret bustle of the tank, the rear overhang of the turret that, in late-series American tanks, was actually designed around the dimensions of the radio. The transmitter produced 25 watts of power and provided a range of approximately 7 miles under good conditions. The radio offered 10 transmit channels selected by the operator, with crystal control ensuring that each channel was held precisely on frequency. A total of 80 channels were available across the frequency range, at 100 kHz spacing. The crystal control deserves a moment's attention because it was as important as the FM in making the system work. A crystal is a precisely cut piece of quartz that vibrates at an exact, stable frequency when an electrical voltage is applied to it. By using quartz crystals to control the radio's frequency, the SCR-508 could be tuned to an exact channel and would stay on that channel without drifting, regardless of temperature changes or vibration. This crystal control meant that a tank commander could select channel 271, meaning 27.1 MHz, and know that his radio was precisely on that frequency, and that every other tank on channel 271 was on exactly the same frequency, so they could all communicate without any tuning adjustment. The combination of FM, which rejected interference, and crystal control, which guaranteed precise frequency, produced a radio that worked reliably inside the electrically hostile environment of a tank. The SCR-508 also provided the intercom system for the tank crew, allowing the crew members to talk to each other over the noise of the engine and the battle, with only the commander able to transmit on the radio to other tanks. The SCR-508 and its variants, the SCR-528 and SCR-538, transformed American armored communications. The radios were installed in the M5 Stuart light tanks and the M4 Sherman medium tanks, and eventually in essentially every American armored fighting vehicle. For the first time, American tank units had radios that actually worked under combat conditions, that could coordinate the movement and fire of a tank unit in real time, that allowed a commander to control his tanks the way the German doctrine had always assumed a commander should be able to control them. The captain at Fort Knox, who had been forced to use hand flags in June of 1940, had, by 1943, a radio that let him give a voice command and have every tank in his company hear it clearly and respond. The American armored force had acquired the nervous system it needed to fight as a coordinated body. The advantage this conferred was substantial and grew over the course of the war. American FM combat radios were, in important respects, superior to the German equipment they faced. The major German army tank and artillery radios used amplitude modulation, not frequency modulation. The German Fuji series tank radios, the Fuji 5 and others, were good equipment by pre-war standards, but they were AM sets, and they suffered from the same interference vulnerability that had crippled the American SCR-245. The American decision to adopt FM, made in 1940 and 1941, gave American armored and artillery units a communication capability that was cleaner, more reliable, and more resistant to interference than what the Germans had. By the later years of the war, this American advantage in combat communications was a real and consistent factor in the effectiveness of American combined arms operations. The Americans, who had started the war with tank radios so bad that commanders used hand flags, ended it with the best tactical radio system in the world. The same engineering effort that produced the tank radios also produced the most famous combat radio of the war, the SCR-300 backpack radio, the original walkie-talkie. In 1940, the War Department gave the Galvin Company a contract to develop a portable, battery-powered FM voice radio for infantry use. Daniel Noble led the project, with Henryk Magnuski as the principal RF engineer and the rest of the team contributing. The challenge was to build a complete FM transceiver, transmitter, and receiver that a single soldier could carry on his back, that ran on batteries, and that provided reliable FM communication in the field. The team succeeded. The SCR-300 operated in the 40 to 48 MHz range, weighed about 32 to 38 pounds, and gave infantry units the same FM communication advantage that the tank radios gave armored units. The SCR-300 was described in its War Department technical manual as primarily intended as a walkie-talkie for foot combat troops, and that phrase, walkie-talkie, entered the language. The radio was first used in combat at the Battle of Anzio in early 1944, and it became standard equipment for American infantry for the rest of the war. It allowed infantry commanders to coordinate their units, to call for artillery support, to communicate with the tanks supporting them, all with the clean, interference-resistant FM signal that Noble's team had perfected. The walkie-talkie became one of the iconic pieces of American combat equipment, appearing in countless photographs and films, carried by the radio operators who were among the most important and most exposed men in any infantry unit. It was a Motorola product, designed by a team led by a former Connecticut professor and a Polish refugee engineer, and it was built on the same FM technology that had solved the tank radio problem. The phrase, learning electronics overnight, is not entirely an exaggeration. The American electronics manufacturing capacity that the war required did not exist in 1940. It had to be created very rapidly by converting and expanding the civilian radio industry. The Galvin Company, soon to be Motorola, was a consumer radio manufacturer that made car radios and home radios. In the space of a few years, it became a major military electronics manufacturer, producing combat radios by the hundreds of thousands. This transformation was repeated across the American radio industry. Companies that had made home radios, car radios, and radio components retooled to make military communication equipment. The workforce had to be trained, much of it female, as the men were drafted, in the precise assembly of complex electronic equipment. The supply chains for components, vacuum tubes, capacitors, crystals, transformers had to be expanded enormously. The quartz crystals alone required a whole separate industrial mobilization, since natural quartz had to be imported from Brazil and processed into precisely cut frequency control crystals by the tens of millions. The American Midwest, the broad industrial region that included Chicago, Detroit, and the surrounding manufacturing centers, was the heart of this electronics mobilization. The same region that built the cars and the tanks and the aircraft engines also built the radios that coordinated them. The automotive engineering culture, with its emphasis on rugged, mass-producible products that worked in hostile environments, translated naturally into the production of military electronics. By the end of the war, the United States had the largest and most advanced electronics manufacturing industry in the world, an industry that had barely existed in its military form in 1940 and that had been built, essentially from scratch, in 5 years. The combat radio program was one of the central pillars of that industry, and Motorola was one of its central companies. The German military communication system, like so much of the German war effort, was technically competent but fell behind the American system over the course of the war, and for instructive reasons. German tank radios were good. The German armored force had pioneered the use of tank radio in the 1930s, and German tanks had been radio-equipped and radio-coordinated from the beginning of the war, which was a major reason for the early German success. But the German radios were amplitude modulated, and as the war went on, the German system did not make the transition to FM for its main combat nets that the American system made. The German tank radios continued to suffer from the interference problems inherent in AM operation. problems that the American FM radios had largely eliminated. There was also a deeper difference in industrial approach. The American system was built for mass production from the start, designed so that hundreds of thousands of identical, interchangeable radios could be built and maintained with standardized components. The German system tended toward higher precision and lower volume, with a greater variety of equipment types and less standardization. As the war became a contest of mass production, the American approach to military electronics proved more effective. The Americans equipped not just their command tanks, but every tank, not just their headquarters, but every infantry company, with reliable radio communication. The density of radio communication in American units exceeded what the Germans achieved, and that density translated into superior coordination on the battlefield. The Americans had more radios, better radios, and a communication doctrine that took full advantage of them. The scale of American combat radio production during the war was enormous. Motorola alone produced well over 100,000 SCR 300 walkie-talkies, in addition to its contributions to vehicle radio production and other military electronics. The total American production of military radio equipment across all manufacturers ran into the millions of units across all the various types: the tank radios, the artillery radios, the infantry radios, the aircraft radios, the ground station radios. The combat radio became one of the most widely produced categories of American military equipment, present in every unit, every vehicle, every command post. The communication network that these radios created was the invisible infrastructure that allowed the American military machine to function as a coordinated whole rather than as a collection of separate pieces. The frequency modulation combat net that the Americans built during the war became the foundation of military communications for decades afterward. The SCR 508 itself remained in service through the Korean War, finally being replaced by the AN/VRC-8 series in the late 1950s. And the company that had built so many of these radios, Motorola, grew from a struggling Chicago car radio manufacturer into one of the great American electronics corporations, a leader in mobile communications, in semiconductors, and eventually in the cellular telephone technology that descended in a direct line of engineering heritage. From the FM mobile radio work that Daniel Noble had begun with the Connecticut State Police in 1939, Daniel Noble's wartime work was only the beginning of a long and consequential career at Motorola. After the war, he recognized the significance of the transistor, invented at Bell Laboratories in 1947, almost immediately, understanding that solid-state electronics would eventually replace the vacuum tubes on which all wartime electronics had depended. In 1949, he established a solid-state electronics research laboratory for Motorola in Phoenix, Arizona, a facility that would grow into the headquarters of Motorola's semiconductor business and eventually become Freescale Semiconductor. Noble's foresight in moving Motorola into semiconductors positioned the company for decades of growth. He rose to vice chairman of the board and chief technical officer of the corporation. Noble received numerous honors, including the Stuart Ballantyne Medal of the Franklin Institute, and in 1978, the IEEE Edison Medal, awarded for leadership and innovation in developing mobile communications and solid-state electronics. After his death in 1980, the IEEE established the Daniel E. Noble Award in his honor. But despite these professional honors, Daniel Noble remained, in the broader public memory, almost unknown. The professor who had built the first college radio station in the country, who had built the first practical two-way FM mobile system in the world, who had led the engineering effort that gave the American military its combat radios, and who had positioned Motorola for the semiconductor age, was famous within his industry and invisible outside it. The radios he had helped create coordinated the armies that won the war, and almost no one outside the field of electronics engineering ever knew his name. The story of Henryk Magnuski deserves particular attention because it captures something essential about the American war effort. Magnuski was a Polish engineer, a graduate of the Warsaw Polytechnic, who had been working in radio and communications in Poland when the Germans invaded in September of 1939. He fled his country as it was overrun, making his way eventually to the United States, where he found work at the Galvin Company. He arrived as a refugee, a man whose nation had been destroyed by the German military, and he was put to work designing the radio frequency circuits of the radios that would help the American military defeat that same German military. He was the principal RF engineer on the SCR-300 walkie-talkie and contributed to the broader military radio program. He held numerous patents over his career and was, by the accounts of those who worked with him, one of the best circuit designers of his generation. Magnuski's story is one of thousands like it. The American war effort, and the American electronics industry in particular, was enormously strengthened by immigrants and refugees, many of them fleeing the very enemies that the United States was fighting. The refugee from German aggression helped build the communication systems that coordinated the American armies advancing into Germany. The openness of the American system to immigrant talent, even in the middle of a war, was one of the structural advantages that the United States held over its more closed and ideologically rigid enemies. His contribution to the radios that coordinated the American ground forces was real and substantial, and like Noble's, it went almost entirely unrecognized outside the engineering profession. The lesson of the American tank radio story is a lesson about the relationship between civilian technology and military capability, and about the speed with which an open, industrially flexible society can convert civilian knowledge into military equipment when it has to. The United States in 1940 had inadequate tank radios, but it had, in its civilian economy, all the elements needed to build excellent ones. It had the FM technology demonstrated in commercial broadcasting and in the Connecticut State Police system. It had the manufacturing expertise developed in the consumer radio and automotive radio industries. It had the engineering talent, both native-born and immigrant. What it had not yet done was assemble these elements into military equipment at scale. When the war forced it to, it did so with remarkable speed. In the space of a few years, the American radio industry converted itself into a military electronics industry, designed and perfected the FM combat radios, and built them by the hundreds of thousands. This capacity for rapid conversion was one of the decisive American advantages in the war. The German military electronics industry was competent but more rigid, more specialized, less able to mobilize the broad civilian electronic base for military mass production. The American industry, rooted in a vast consumer electronics market and an industrial culture oriented toward mass production, could expand and convert with a speed the Germans could not match. The tank radio was one instance of a general pattern. American civilian technological capability, when mobilized for war, produced military equipment faster and in greater quantity than the more militarized but less industrially flexible enemy economies. The radios that coordinated the American armored and infantry forces were the product of this mobilization, and they were as decisive, in their quiet way, as any tank or aircraft. In a war decided by what could be coordinated, what coordinated the American forces was the FM combat radio. It was invisible, hidden in the turret bustle of the tank, or strapped to the back of an infantry radio operator. It produced nothing photogenic. It appeared in no famous battle as a protagonist. But it was the nervous system of the American ground forces, the network of clean, interference-resistant voice communication that allowed American units to fight as coordinated bodies rather than as collections of individual vehicles and men. The captain at Fort Knox in June of 1940, forced to use hand flags because his AM radio was drowned in static, was fighting the way armies had fought for centuries. The captain in Normandy in 1944, giving a voice command that every tank in his company heard clearly through their FM sets, was fighting a new kind of war, a war of real-time coordination that the radio had made possible. The radio came from the civilian economy, from a professor who had built a college radio station and a state police communication system, from a car radio company that learned to build military electronics, from a Polish refugee engineer who designed the circuits, from the vast industrial capacity of the American Midwest that converted itself to military electronics production almost overnight. It came from a society that had more radios, more radio engineers, more electronic manufacturing capacity than any other on Earth, and that converted that civilian capability into military capability with a speed that its enemies could not match. The Germans had pioneered tank radio, but they stayed with AM, and they fell behind. The Americans, who had started the war with tank radios so bad that commanders used flags, adopted FM, mobilized their industry, and ended the war with the best tactical communication system in the world. In a war fought between industrial systems, the system that could turn a car radio company into a military electronics powerhouse in a few years was the system that won. Daniel Noble, the professor who understood FM, and Henryk Magnuski, the refugee who designed the circuits, and the thousands of mostly female assembly workers who built the radios, and Paul Galvin, the businessman who bet his company on military electronics, together produced the communication network that coordinated the American war machine. None of them is famous. The radios they built are forgotten, hidden inside tanks that are themselves remembered for their guns and their armor rather than for the FM sets that made them part of a coordinated force. But the radios were the difference between a tank that fought alone and a tank that fought as part of a team, and in the end, the teams won. The FM Combat Net carried the American armies from Normandy to the Elbe and across the islands of the Pacific, and it kept working, channel by crystal-controlled channel, clear through the static that would have buried any lesser system. That was enough. In a war decided by what worked, the radio worked, and the coordination it made possible was, quietly, one of the things that won the war.